First of all, let me introduce to you. I'm Giulia Malinverno, a research engineer from Motor Design Limited, and today I'm going to present how to build your workflow between MotoCAD and other tools in order to design and study any machine. We will cover different topics. First of all, we'll start from a quick introduction to Motor Design and MotoCAD. For those of you that couldn't join the previous webinars, we'll speak about the needs that brought us to create different workflows with other tools. By starting from that, I'll introduce you to the different links with ANSYS Maxwell. First of all, the improved 2D export for parameterized geometries, the brand new 3D export for BPM and induction motors, the capability of MotoCAD to import custom DXF created or modified in ANSYS Maxwell, the functional mockup interface, so-called FMI, for both electromagnetic and thermal models, but that can also be used in combination between the two of them. And then we will cover the Simscape export in order to export a permanent magnet synchronous motor in terms of flex linkage. And then we will conclude with the new MotoCAD feature to calculate the electromagnetic forces within an electrical machine, and then how they can vary within the time domain. So let's start then with a quick introduction to Motor Design and MotoCAD software. MDL is a UK-based company founded in 1999 by Dave Staten. It has a worldwide customer across the 6 industry main sectors and the university partnership as well. Our software development team develops MotoCAD, which is the world leading tool for the design and analysis of electric motors. And thanks to the high level of engineering know-how, our expert electric machine designers work in both consultancy and research projects in order to design and analyze electric motors, as well as support customers. We collaborate in several government and EU-funded research projects, as well as university worldwide, in order to develop electric modeling techniques and create new validation data. So let's start with the introduction to MotoCAD. MotoCAD is our software dedicated to the design and analysis of electric motors. It covers all typical types of radial flux rotating electric machines. It enables rapid and accurate electromagnetic, thermal, and mechanical analysis of electric machine across the full operating envelope. It has a quick evaluation of motor topologies and produces design which are optimized for cost, performances, efficiency, and size. One thing that is worth to say, it's its practical approach, since enabled even non-expert in electromagnetic or heat transfer to easily study the machine's performances and the cooling. MotoCAD has 4 different modules: electromagnetic, thermal, lab, and mechanical. The electromagnetic module combines 2D transient finite element and analytical method to calculate the machine's characteristics. It computes outputs such as torque, efficiency, power, and torque ripple. The thermal module calculates the temperature of the motor components in both steady state and transient conditions. It generates thermal and flow network automatically. It includes radial and axial heat transfer in a 3D network, and above all, enable accurate modeling of thermal behavior within seconds of calculation. The lab is a virtual testing laboratory of MotoCAD. It enables the analysis of a machine's performance over its full operating range. The outputs, such as efficiency maps, torque speed curves, loss maps, and drive cycles, are rapidly generated. And by coupling the lab with the thermal module, lab is able to predict the thermally constrained continuous operating envelope and analyze the temperature raise over driving cycle. Finally, we have the mechanical module, which has been recently introduced. It's a 2D finite element solver, which enables a rapid evaluation of the stress, strain, and displacement in rotor caused by the centrifugal forces. So now that we have introduced MotoCAD, we are going to answer the question, why do we need workflows with other tools? So the design targets are often specified at a system level, as for example, the efficiency, cost, volume, and range. And to meet these requirements, the motor cannot be designed in isolation, but has to account for a wider system level simulation, since it allows to ensure the optimum design outcome. So for this reason, we started from this reason, MotoCAD is linked to complementary software solution through dedicated workflows. MotoCAD is primarily used by electric machines designers in the early stages of the project, since it's particularly useful for initial design, topology selection, sizing, and optimization across the full operating envelope. But if the user would like more detailed physics-based analysis, especially in the later stages of the design process, MotoCAD provides several links with other CA tools through dedicated workflows and interfaces. So, as we already mentioned, MotoCAD is primarily used by electric machine designers since it's particularly useful for initial design and optimization across the full operating envelope. It provides a link to Maxwell for advanced magnetics modeling, but also to other packages for more detailed physics-based analysis in the later stages of the design, for example, ANSYS Maxwell. But it can also be linked with other tools for system design and validation in order to simulate the behavior of the machine with an electric drive. So now we can start to have a look at the different workflows between MotoCAD and the other tools. But let me mention first that most of the features that I'm going to show you today will be available in the new MotoCAD version 13, early next year. So let's start with the first example of workflow, which already existed in MotoCAD, but in version 13 it will be available, the improved export for 2D design, as well as the brand new 3D export. The user will be able to choose between two different export solutions and geometry formats, which means choose to export the machine with outlines or outlines and stator template. In the latter case, the stator will be exported by using UDP, which means user-defined primitive, which are available in ANSYS Maxwell, and enable the user to create and parameterize complex geometrical objects using inbuilt templates. In this way, the user will be able to modify geometry parameters in order to study how the changes will affect the results, and will have a greater flexibility with the geometry. It will also be possible to choose between an automatic solving or not. In the first case, the script will solve automatically the model and create a transient report which will include the main parameters such as induced voltages, input currents, flex linkages, and torque. So once the user has made his design in MotoCAD and is happy about it, it will automatically export a VBS script in the selected folder path. And then to get the design model, the script needs to be run in ANSYS Electronics Desktop, and it will take a few seconds to complete the process. So the script will automatically generate all the elements of the machine and import all the materials from MotoCAD materials library. The analysis will be set up as in MotoCAD based on the number of points, number of cycles, speed, and number of folds. Phases excitations, boundaries, and motion step will be automatically applied as well. And if the user will choose to export the stator with UDP, with the user-defined primitive, this will be parameterized as in MotoCAD. By using the UDP, we can define the slot geometry, such as the slot width and length, as well as for the slot opening and wedge. So as we can see on the right bottom side of the slide, ANSYS Maxwell also gives greater flexibility for the slot type geometry. In fact, there are several shapes to choose from, and this can be done just by setting the number which refer to that shape. The improved 2D export will also be available for induction motors. The user will have the choice to export the parameterized stator or not, but in addition, the rotor lamination and bars will be parameterized by using UDP as well. So as it is for the stator, also for rotor and bars, the slot geometry will be automatically exported as in MotorCAD by keeping the same depth and width. The ring will be modeled by using the end connection option, which basically assign the end ring resistance and inductance to all the rotor bars. This procedure has to be done since it's not possible in a 2D design to model with a UDP the end ring. So the resistance and inductance for the end ring will be automatically retrieved from MotorCAD by the script. Here we have the brand new feature in MotorCAD version 13, which will be the automated 3D export, which could be a valuable investigation for 3D effects such as leakage and winding inductances and 3D effect in general. So as it is for the 2D export, the stator can be exported by using UDP. So different axial lengths can be set for stator, rotor lamination, and magnets. Excitation, motion, and analysis setup will be automatically applied according to MotorCAD. But one point that I like to highlight is the symmetry multiplier. So since the 3D models may be computational demanding, the script uses the symmetry of the motor and half of the axial length in order to reduce the computational time. As we can see at the right bottom side, the symmetries option are taken into account in the design settings properties. So the user will get the same result in less time. And it's also worth to say that the same symmetry factor can be applied in the 2D model as well. Every model will always have 3 different bands in the air gap with 3 different diameters and axial lengths in order to have a good resolution for the mesh in the air gap. The bands need also to include all the rotating parts since they play an important role when the motion setup is given. Exported models will always be inside another band called region, which has to be filled with air, otherwise we couldn't get any acceptable results. The export gives a great flexibility to the user since it allows to change the parameterization of different elements such as coils, stator, and bands. Furthermore, it will also be possible to change and refine the mesh length for each object of the model. So one of the reasons to parameterize the stator lamination and coils was the quick implementation of the skewing, because depending on the skew angle set in MotorCAD, the script will automatically apply it in the exported model in ANSYS. So if the user would also be interested in rotoskew, in MotorCAD is possible to implement the step skewing by setting the desired number of slices. And in this case, the generated script will export it automatically and set in a 3D model. For model with the skew applied, which I mean both stator and rotor, the exported model by the script will always be the whole model without taking into account any symmetry. So now let's have a look at the step skew for the rotor lamination. So as you see at the top of the slide, depending on the number of slices, MotorCAD will apply the skew angle in mechanical degrees, but this can be customized depending on the user needs. The rotor step skew has several powerful features, and let me mention some of them. First of all, the magnet magnetization, where each magnet will have its own relative coordinate system, which refer to the magnetization. As you can see from these pictures, each magnet will have its own coordinate system, renamed depending on the number of slices and magnets. Then we will have the insulation boundary condition between each slice. This condition is used to model very thin sheets of perfectly insulated material between touching conductors. Is an important feature because the insulation prevents the current to cross the boundary. So in this scope is used to control the flow of induced eddy current. So the 3D export can also be a good tool to investigate the magnet losses. So since the user may have the need to apply several steps queue, or the motor has a high number of poles, the names of each object can get confused in the exported model. So in order to avoid this, the script will enumerate each slice and each magnet of the slice in a consistent way in order to have consistent names. As I already mentioned in the previous slides, for the 2D export, the 3D one for induction will be available in the next MotoCAD release. And as it is for the 2D, every component will be parameterized for the induction motors, such as a stator, rotor, bars, and end ring. In the 3D, there's no need to assign the end connection option to model the end ring and connect all the bars, since we are using the squirrel cage UDP to model bars and end ring. Also for the induction motor, the skew for stator, rotor, and bars will be automatically applied, since the use of UDP makes the implementation easier. So just to conclude, both 2D and 3D exports are powerful tools to study the machine behavior, and the parameterization give greater flexibility to the user to change the geometry in order to study different solutions. But I'd like to focus on one point, that the export can be used even by non-electrical machine designer or non-expert in the sector, since the user will need to simply generate a script in MotoCAD and then run it in ANSYS Maxwell. Another important feature in MotoCAD is the import of DXF geometries, which gives a very fast estimation of the electromagnetic performance with sufficient accuracy. DXF can be created and modified in ANSYS Maxwell. So once the user is happy with the design in ANSYS Maxwell, it's possible to save the model in DXF format and then import it in MotoCAD. There are several DXF import options for the electromagnetic module. For example, single slot and pole, single rotor pole, single stator slot, entire stator and rotor, entire rotor, and entire stator. So sometimes the user has to be very precise with the machine geometry, and it can be tricky to exactly reproduce the geometry by using the parameter model in MotoCAD. So sometimes it's needed to simulate the exact geometry, for example, including flex barrier, for an accurate prediction of torque ripple. So for this purpose, MotoCAD allows the import of DXF geometries to use in FEA simulations. It's important that the MotoCAD parameter mode matches the DXF geometry as closely as possible. Hair gap thickness and location is most important, since this is defined by MotoCAD geometry for the FEA simulations. Here we have another useful coupling provided by MotoCAD, which is the link with the FMI, which means the Functional Mockup Interface, which is an open standard for exchanging dynamical simulation models between different tools in a standardized format. The FMI standard specifies the FMU, which stands for Function Mockup Unit, which is a file with the extension .fmu that contains a simulation model that supports the FMI standard. It enables system-level co-simulation of MotorCAD models. Both thermal and electromagnetic can be run within a dynamic system-level co-simulation. And this allows fast and accurate simulation of electrical machine in order to be incorporated in a wider system-level model. The EMAG and thermal FMU can be modeled as single entities or coupled models, where one's output will be the other's input, as we are going to see later on in the next slides. To do it, we use MATLAB Simulink environment to demonstrate its functionalities. You can see from the top right side of the slide that the FMU needs to be imported in a Simulink environment from the library. Then the FMU name needs to be specified in this file with the format .fmu, which will be available in the MotorCAD folder installation. The FMU requires that an existing mod file, which is the MotorCAD file, is passed into it, and when a system simulation is run, MotorCAD is used to perform a transient simulation. For each time step of the system simulation, the inputs are first evaluated, passed to the MotorCAD model, and one time step of the simulation is performed. The outputs so are calculated based upon the machine mod file, the current time step, and previous iterations. This procedure is valid for both the electromagnetic and thermal one, and therefore allows dynamics interaction between the interconnected systems in order to be co-simulated. The inputs can be exported from the duty cycle calculation in MotorCAD Lab as a math file, which basically defines a matrix. This can be imported in MATLAB Workspace, and those values can be imported in the FMU as well by using 1D lookup tables, where the user needs to specify the number of the column which refers to that input in the FMU. Within the Simulink environment, the MotorCAD FMU appears as a block with the inputs on the left side and outputs on the right, which of course are going to be different between the thermal and the electromagnetic one. Here we can see the inputs of the EMAG one, which can be basically divided in DC bus voltage, speed and torque demand, temperatures such as stator windings and magnets, and the maximum DC current, which is the maximum available DC current in lab electromagnetic calculations. The user will have to import the inputs in the MATLAB workspace, which are going to be evaluated in 1D lookup tables, and all of these are connected with the clock in order to evaluate each input step by step, since the time step will be set up in the clock as well. The output are labeled with ports and renamed based on the output to be evaluated. This procedure is needed in order to spot them in the simulation inspector, this one in Simulink, and allows the visualization of each output as you can see here for the shaft power. Here we have the thermal FMU. The inputs required can be split in the following categories. The losses for individual loss components, the temperatures such as the ambient, fixed temperature boundaries or the cooling fluid, speed for any speed dependent properties, volume flow rate for any active cooling fluids, and then the pressure for characterizing a cooling fan if this option is used. The outputs of the thermal one can be divided in machine temperatures, where any node within the thermal network has to be included as a probe. The resulting cooling fluid temperature and pressure based upon the coolant input parameters, machine geometry, and power dissipation into the cooling fluid. The results of the transient thermal simulation are presented, where at the top we can spot the MotoCAD thermal transient result, and at the bottom the one from the FMUs. So here we have a good example on how it will be possible to have a combined link between the two FMUs. For example, the output losses from the IMAG one can become the inputs of the thermal one, and the output temperature of the thermal one can become as well the inputs of the IMAG one. But this is just an example, and of course the user can link them together based on the needs. So we can now start to speak about another useful link between MATLAB Simscape and MotoCAD. The link exports a permanent magnet synchronous motors in terms of flex linkage as a function of current and rotor angle into the FEM, which means finite element method, FEM parameterized model in Simscape, which allows the machine to be included in a larger system level model. So first of all, the user needs to set up the permanent magnet synchronous motor model in MotoCAD with the necessary geometry, drive, winding pattern, and materials. Then the user needs to define the FEM parameterized model in Simulink as a 3D flex linkage. This choice allows to provide the flex linkage data in a variety of formats. Here we have an example on how to implement the model in a wider system level simulation. Here we have an open circuit test in order to show the nonlinear back EMF characteristics. So as I already mentioned, the user can provide flex linkage data in a variety of formats, which can be tabulated DQ flex linkages or A-phase flex linkage data. They can be tabulated using Cartesian or polar coordinate or polar current coordinates. The Cartesian tabulation implies the flex linkage tabulated in terms of DQ axis current plus the rotor angle. Instead, the polar tabulation involves tabulating flex linkages in terms of current magnitude, current advance angle relative to the Q axis, and the rotor angle. So in this picture, there's an example of electrical inputs with DQ flex linkages data format defined in terms of current magnitude, current advance angle, and rotor angle. And the user needs to specify them as vectors. So except for the current magnitude, the length of the other vectors is defined by the number of points per cycle, which is defined in MotoCAD inputs data. And this number will affect the accuracy of the result. So of course, greater is the number, greater is this number, better will be the accuracy of the result, but longer will be the simulation. The script, the MATLAB script passes the combination of these vectors to MotoCAD, calculate the electromagnetic performances of the machine, and for each combination it retrieves the value of the torque and fluxes, and then store these values in matrices. At the end of each cycle, we will have the data stored as 3D matrices, as we can see on the right side of the slide, defined in terms of current advance angle and rotor angle. Here we have the new features for force analysis, which will be available in version 13 of MotoCAD, and it will allow the user to visualize electromagnetic forces within an electrical machine and how these vary with the time domain. This allows for a basic idea on how the machine will behave from noise and vibration, and is a good starting point for further NVH analysis in the future. The export currently works for 4 machines type, BPM, outer rotor BPM, synchronous, and switch reluctance. A new visualization in the output data will be available based on the different force harmonics animation and harmonics visualization. So of course, for these new features, new parameters have to be set up for the NVH force animation, such as, for example, the number of steps and force points, enable the transient force calculation, and finally define the parameters for the force animation, such as the number of slices. There will be a new output data interface for both on-load and open circuit force animation, commands to start, stop, and pause the animation, the current step in cycle, the animation selection, which refers to the harmonics displayed, the repetition command over multiple cycles, and the ability to export GIF with custom size at set speed. Now I'm going to present you two different designs. The first one is 12 slots 10 poles, and the second one is 12 slots 8 poles. Here we have the 12 slots 10 poles, and we can see the force animations as will be displayed in MotoCAD, where the first one represents the total harmonic content, and the others the animation for each harmonics up to the fifth one. Instead, here we have the second configurations, 12 slots, 8 poles, and as it was before, the first one displayed the total harmonic content, then the other, the 8th and the 16th harmonics. We will have a new visualization for both radial and tangential harmonics. And here is presented the harmonic amplitude content for the first combination, 12 slot 10 pole. Here instead we have the same radial and tangential harmonics, but for the second one, for the second combination, 12 slots 8 poles. So at this point, it's also worth to mention the different format that can be exported from MotoCAD, which are MOT, text, and JSON file, and this can be used and imported by several other software to carry out further NVH analysis, such as, for example, ANSYS Mechanical, Romex Suite. But these are types of format file that can be used by other software as well. Okay, so now that the webinar is finished, we have some time to spend to answer questions. So as I mentioned at the beginning, the webinar is interactive, and I already got some questions from you while I was speaking. So let me answer. I pick up this question. Let me answer to the first one, which is asking when all these new features will be available. So as I mentioned, they will be available with the new release of MotoCAD, the version 13, early next year. As it has always been, the version will be constantly updated throughout the year. So there might be some minor and major improvements and other new features as well, of course. The second one is about the ANSYS workflow. Is asking if the results from the 3D study, from the 3D design, can be used or imported in MotoCAD in order to calibrate the model. So yes, this can be done. Let me mention one example. So for example, by exporting the 3D model, the user can study the unwinding effects for different stator and rotor lamination lengths. ANSYS Maxwell allows to calculate the self-inductances per phase, and the user, for example, can compare those results with the 2D one, and depending on the calculation method in MotoCAD, which can be set to Hanselmann or Rosengrover, we can come out with adjusted the inductance multiplier to apply in MotoCAD in order to be as closer as possible to the 3D results. So yeah, this was one example. Another question. Yeah, the question is is asking if it's possible to export a thermal resistance network from AutoCAD. Yes, this is possible. So during the webinar, we focus on the workflow between ANSYS Maxwell and AutoCAD. But AutoCAD can be interfaced with various engineering software packages for post-processing operations. Another example could be the workflow with ANSYS Twin Builder, which is the formerly Simplorer. This allows to export a thermal resistant network from AutoCAD to ANSYS Twin Builder by using the AutoCAD matrix export functionality. So this allows the matrices using AutoCAD Solver to be exported to use with other system level simulation. So after solving the thermal models, the resistance, capacitance, and power matrices can be exported. And a Python script will generate the SML file to be imported into Twin Builder. The script mainly consists in input data and computational operation for the exported matrices. In the input data, the user will have to specify the project name, the directory where the AutoCAD matrices are exported in, and the terminals. So once the user has refined his Python script, the model can be imported then imported in Twin Builder. Once the model will be ready, the terminals can be, for example, connected to measurement points, similarly to set the boundary condition, for example, ambient and housing water jacket temperatures. We still have space for one last question, which is about the FMU. Is asking if the user needs a proper license to use its functionalities. The answer is yes. So we are working on a solution for the user in order to use this functionality with the AutoCAD interface and with the already existing license they have. Okay, so it's now time to conclude this webinar. But first of all, let me mention some important information. Since we got many questions during the webinar and I didn't answer to all of them, we will do our best to quickly respond via email to any question. If you also have any kind of feedback, please contact us on the email address shown here. Our team will send an email within a week containing the link to the webinar recording. And then just as a follow-up, before close the session, let me mention our user conference in Birmingham in February 2020, where for those of you interested, there will be proper workshop sessions, presentation about new features, and dedicated session for answering any further questions. So follow the link at the bottom of the slide to discover more about the upcoming events. So now it's time to conclude the webinar. Thank you for joining us and hope you enjoyed it.